Welcome back. We are in chapter 5, and this will be the first 2 years biosocial development. This begins a new pattern in the textbook where we will be doing clusters of 3 chapters that will cover the same age bracket, in this case, the first 2 years. One chapter will be devoted to biosocial development, one will be devoted to cognitive development, and one will be devoted to psychosocial development. So you'll get into a little rhythm where you see the same kind of organization across each age group. All right, well, let's get started with the first 2 years. All right. So, in the biosocial development, we're talking about all the biological factors that contribute to development. So in the first 2 years of life, we're going to focus on the kinds of physical development that's going on with the body, with motor skills, with perceptual skills, things like that. There are 3 basic patterns to the physical development that we're going to observe. The first one is what we already referred to in our earlier discussion of prenatal development, and that is the cephalocaudal pattern and the proximodistal pattern of development will continue. These are my children dancing around after a bath. This picture's got to be 25 years old. I put little sticky notes over the print so that you're not seeing them naked, which is what they were, but they're babies. And he is probably around 1 and she is around 4. And what I wanted you to see in this picture is how the 1-year-old has such shorter legs and shorter arms relative to torso than the 4-year-old does. So that's a great example of, the proximodistal development. His torso is much more developed relative to his appendages. And then also the cephalocaudal development. Notice how big his head is relative to the rest of his body compared to how you can't really see her head that much, but you can infer from the hair covering her face and stuff. Her face is a lot smaller compared to the rest of her body. And that's going to continue to the point where in adulthood, the head is going to look a lot smaller relative to the body than this 1-year-old is showing. Interestingly, even though our heads are much smaller by adulthood than an infant is, our head to body ratio is still much larger than other animals. We have very large heads relative to our bodies. So imagine that. That means that a toddler, an infant, has a really big head relative to other animals, like a giant head. Here's another picture of my son. This time he was actually wearing a diaper. When we talk about infant development, and actually development pretty much until adulthood, we experience something called canalization. Canalization is referring to the tendency for all the members of the species, in this case humans, to follow the same basic developmental trajectory, independent of genetic background, independent of context. The same basic pattern will follow. And we're going to see that in when we discuss norms and other things that depend on canalization. If it weren't for canalization, if it wasn't for the fact that we all follow the same basic trajectory, developing like motor milestones at certain ages and things like that, there's no way that we would be able to establish norms for what you can expect your baby to be doing at different months and things like that. So canalization is a really important pattern that contributes to physical development and allows us to describe physical development. And then differentiation and integration is the third basic pattern. And what we're going to see is that with maturation, as development proceeds, there's going to be a tendency for skills to get more and more specific and to be able to work together to achieve goals. So I've got a picture here where somebody's having to help the baby to sit up on the left-hand side, and then ultimately the baby can integrate all the balance cues that are necessary to ultimately hold themselves up. As the baby develops into a child, you're going to start to see that motor behaviors like reaching become much more specific. The small infant will reach with a lot of variation in the path of their hand toward the object that they're trying for. As they get older, they'll be able to be much more specific and literally have a straight line between where their hand started and where it landed to grab the object. So we see this, differentiation where the behaviors get more specific, but then also integration so that they can integrate, like a baby infant will reach for an object with their hand closed. And then when they get there, they're almost like a robot who has to go, open hand, and then hand opens up, and then close hand around object, and they grab it, and then they retrieve hand. It's all very, robotic, really, honestly. And as they get older, they'll be able to integrate reaching, opening hand, grasping, pulling arm back. They can integrate that all together into one smooth movement. So that's just an example of what we mean by this differentiation and integration that will be happening as the child goes from infant all the way into adulthood. Now, I mentioned a second ago the word norms. Norms are very much dependent on canalization, this idea that all the members of the species will follow a basic trajectory. I thought I'd share with you a couple of examples of norms that come. This one comes out of our current edition of the textbook. So we're seeing, norms for weight for boys and for girls. And so if it weren't for the fact that all the babies kind of gain weight in a similar way, if it wasn't for canalization, we wouldn't really be able to make meaningful norms. Like, it would all just be random. Your baby will be whatever size your baby's supposed to be, right? But that's not how it is. Babies tend to grow in a, very continuous and consistent way. And so we can establish these kinds of norms. So that's one example. Another example of norms would be the acquisition of what we call gross motor skills. We'll talk more about this in the next age bracket, but gross motor skills are, being able to move your large muscles, to sit, for example, to stand or walk, to run or to jump. Those are gross motor, big muscle skills. So we have two columns. One says, this is the age when 50% of all the babies who have been measured have achieved this skill. And the right-hand column is when 95% of all babies have mastered the skill. So part of the reason why norms are so important is because if you have a baby who is, let's say, 5 months old and is not yet able to sit with their head steady, then you know that there might be something wrong. Like, that's a really important aspect of norms, is to help us to identify someone early on that might be having a problem. That's a really important function of norms. A not important function of norms is for parents to look and see if maybe their baby's ahead. And parents do it a lot. They're like, oh, only 50% of babies can sit up with their head steady at 3 months of age. And my baby's doing it at, 2 months and 3 weeks. So my baby's somehow advanced. My baby's magic. And the truth is, babies develop in sort of fits and starts. And so that early head steady sitting might be a predictor of great motor skills, or it might be a predictor that, they may go back onto the norms level, and it might be 6 months before they can sit unsupported. So they could hold their head steady, but they're back to normal for unsupported sitting. It doesn't really mean anything to have a baby that's ahead. A lot of people think it does, but it doesn't predict anything to have gross motor skills that arrive early. It does mean something to be well behind. And so that's why norms are developed and referred to, is just help to eliminate concern, is what it's really about. All right, well, enough about that. Let's talk a little bit about brain development, because this is really important. A lot of brain development occurs prenatally, but if our brains were as well developed as they should be, the head would not be able to pass through the birth canal. Like, the brain would be too big. So a lot of brain development has to happen after birth. So let's talk a little bit about infant brains. At birth, babies don't spend any time in what we call alpha waves. Electrical activity is measured in the brain because the way that our neurons communicate with each other is basically electric. And so we can detect electrical impulses. And when a person is relaxed but awake, very, very relaxed but awake, their brain enters alpha waves. So if you've ever been just completely like vegging in front of the TV set and literally you can't even scroll Instagram at the same time, like, I'm just going to sit here and stare, you're probably in alpha waves. You probably have moved into that. If you've ever been laying in bed getting ready to fall asleep and you're just sort of completely relaxed and trying to doze off, probably you were in alpha waves. Newborns don't experience that state of consciousness. They are either awake or they're not awake. Their brain is either active or it's in a sleep state. It's not ever in this sort of awake but relaxed. Kind of explains a lot about newborns because they don't ever seem to be awake and relaxed. So it's because that's how their brain works. Now, the cerebral cortex is the outer layer of the brain. Here's a baby's brain, and everything that you can see that has an arrow pointing. So you see these like lines that I cut off the labeling of it because I'm not trying to teach you the names of the lobes. I just wanted you to see them. Everything that has lines pointing to it, that's all cortex. That striated part that's below it, that's cerebellum. That's not part of your cortex. That's part of the brainstem. The cord that's going down the bottom, part of that is your spinal cord. The very upper part of it is your pons and your medulla and stuff. So I'm not talking about that part. I'm talking about the part that's on the top, and I'm going to use my arrow and hopefully you can see it. This is all cerebral cortex. So this part that's shaded a pink color is cerebral cortex. Unfortunately, this parietal lobe, temporal lobe area is the same color as the brainstem areas, so it's hard to use that as a descriptor. But the teal blue part in the back, that's your visual cortex. So all of that curvy stuff that's at the top, that's your cortex. It's about a few millimeters thick, and it contains billions of neurons. But at birth, it contains more neurons than you're going to have as an adult. And in fact, during the period of time between birth and 4 years, you're going to grow even more neurons in your cerebral cortex. After age 4, they'll start to prune back. But for right now, from birth, this little baby brain is developing a bunch of neurons every day, building up that cerebral cortex. So it's very undeveloped at birth, but it's really important to know that experiences that the infant has will help to shape which neurons will be preserved in this big burst of neurons that are growing. So let's talk about neurons for a second, because I'm assuming most of you have had introductory psychology and have seen this, but and maybe some of you have even had A&P and maybe have seen this. But your brain is made up, the cerebral cortex is made up of a bunch of neurons. They're regular cells with a cell body and DNA and things in it. But what makes them different, what makes them really unusual, are the branching fibers that are really visible and noticeable on these neurons. The dendrites are the branching fibers that collect information from neighboring neurons. And then also you have dendrites that reach out to your sensory organs. So you have dendrites that collect information from the ears and the eyes and your tongue and your nose and like that. You even have those dendrites that reach down your spinal cord to collect information from touch. So you have dendrites that are really, really long that collect information from your sensory organs, as well as collecting information from other neurons. And then you have that other branching fiber that is coated in what looks like it could be, a beaded necklace, it looks like, right? Because it's got those sort of elongated beads on them. And that's that's the axon, which is the part of the neuron that's going to send information from the cell body of the neuron to the neighboring cells or to any kind of voluntary muscles or like that, wherever information needs to be sent. So the way that your brain appears when you're really little is that you grow a bunch, in infancy, you're going to have a bunch of neurons, and they're all connected to each other at these structures that we call synapses. That's what's shown in this little box here, is where the sending axon butts up against the receiving dendrite and communicates using chemical messengers called neurotransmitters. So when you're little and haven't had a lot of experience, all of your neurons are just sort of lined up and they're communicating and they're just passing information along. They aren't necessarily sort of specified to only respond to certain kinds of stimuli or certain kinds of ideas or things like that. That will happen with experience. And with experience, certain neurons will be deleted. The connections between other neurons will really become strong. And that's how we represent memories. And that's how we really represent our world, is by organizing our brain to represent the kinds of experiences that we've had. So right now in the 0 to 2-year-old phase, a lot of growth is happening. A lot of neurons are being born and are organizing and getting connected. But at the same time, connections are being strengthened in certain pathways. They start with the pathways that govern eating, bonding, all of those kinds of things. That's where the pathways are usually really very early on are being set up. But with experience across the lifespan, you'll continue to prune neurons, make connections, and represent your world as best as you can with your brain. So in this panel, what you're seeing is how much growth there is in different parts of the brain by age. And so everything that's to the left of the black dotted line is in the first year of life. And so you'll see that the purple curve, which represents the visual cortex and the auditory cortex that are devoted to processing information from your eyes and processing information from your ears, that grows enormously in the first few months after birth. So you see, and actually you see some before the first month, right? Because a lot of this happened in the womb, especially for hearing. So you see all this cortical development in the very early part of the first year, and then it slowly drops off across the rest of the first year of life. The red hump there is referring to the development of the speech areas. So you've got one part of your brain, and in fact, if I go back to this baby picture, here's my baby, there it is. The purplish area that's like a half circle there, that's the part of the brain that's devoted to what we call receptive speech. So that's the part of our brain that translates what's coming in from our ears and turns it into language so that we can understand it. The line that's pointing towards the pink part of this baby's brain is pointing at the part of the brain that processes outgoing speech, right? That produces speech. So when we look at, this red line, those areas are developing most heavily in the second half of the first year of life. So you see like this really peak of really developing those language areas. And the first part to develop is the receptive language area, what we call Wernicke's area. And then later in the first year of life, Broca's area that will control the production of speech will start to develop. And this helps to explain why infants seem to understand what you're saying to them long before they can respond to you in a verbal response. Now the yellow bar, what you can see is that, this would be the prefrontal cortex, the part of the brain that handles higher order functioning. That's really the quintessentially human part of the brain. Other animals, even our closest cousins, don't have this prefrontal cortex that's as big as ours, and it takes a long time to develop. And so you see that the highest rate of forming synapses and growing our dendrites happens between about 5 and about 12 years of age, 8 years of age, something like that. But honestly, that part of our brain doesn't fully mature until we're in our 20s. Depending on your sex, females tend to mature a little earlier, males a little bit later as far as the prefrontal cortex, the part that really helps us to make good logical decisions. So the synapse formation, the dendrite formation really peaks in childhood, but it continues to grow and hone and do the things it's supposed to do well into the 20s. Now, lateralization is another issue that we want to get to. So I'm going to go ahead and take a break here because I'm going long, and I'll come back and we'll talk about lateralization in the infant brain.